Moving on to the final part of this week's lecture, we're going to be looking at a multi-force problem. Up until now, we've had a fulcrum problem that you balanced a load, an external load, with an internal force generated by your muscles or a force that you apply, and so this is a two-force problem. Now we're moving into several forces. For example, the figure shown in this slide is somebody stooped over working on a table. You can see that his torso is stooped over, his arms are reaching out, his head is pretty far in front of his spine, and so you know that that posture is not going to be a very good posture. It places a higher stress level on your back, on your lower back, to make you more susceptible to a potential back injury. And so we're going to be looking at how much force is placed on your lower back. So we want to calculate that, and we want to find out how hard are the muscles, the extensor muscles, working behind your spine. In this case, we're going to have an imaginary lever running through the lower back. The lower back, where most higher number of injuries occur related to material handling. The problem area in your back is typically where your fifth lumbar and first sacral vertebrae meet. And so we're going to put the fulcrum right there. We're going to consider the body weight associated with each of these body segments, your trunk, your arm, your head. So you can see that that'll cause a counterclockwise moment about the L5-S1 vertebrae. To counteract your body weight, there has to be some muscles acting, in this case extensor muscles acting behind the spine to counteract this motion. Otherwise your body would just flop forward. Okay, so we're looking at the balance between all of these forces. The person weighs, the operator, the employee weighs 600 newtons, so that'll be a body weight. What you're given in this problem, and I admit I stole this problem from another textbook, but you're given what the weights of these body segments are, and these are in biomechanics, these are known, these have been measured 10, 20, 30, 40, 50 years ago. They're usually provided in a textbook. They're given as a percentage of your body weight. For example, your head weighs 8.4% of your body weight. If this operator's body weight is 600 newtons, then the 0.84, to find what the weight of the head is, we're going to look at the using that percentage is 0.084 times our 600 Newton body weight. We find that the head weighs 50.4 newtons. Okay, so 50.4 newtons. The arms are 5.1% of your body weight. Again, doing that same thing, changing 5.1% into decimals, 0.051 times the body weight of 600 newtons. You find that your arms weigh 30.6 newtons for this operator. And lastly, his trunk, sometimes I'll change it, I might say torso, but his trunk weighs 50% of his body weight, and so 50% of 600 is obviously 300 newtons. Okay, so we have those loads, we'll use those as forces. We're trying to find E, what's the extensor muscle effort. We also need to know, as we're looking at balancing these things, that the distance between the fulcrum to each of these loadings. So distance between the fulcrum to the torso, and we place the full loading of the torso, the 300 newtons, again we place it at the center of gravity of the torso. And again, that is something that's been tested many years ago, usually provided in a textbook. The center of gravity of a body segment. That'll be 0.13 meters in front of the L5-S1 joint. And so this is 0.13. For the arms, it'll be this distance, scribble that out, just the distance to the spine out to the center of gravity of the arms. That's going to be 0.3 meters. And then his head, the center of gravity of his head, just like we did whenever I was showing the first, second, and third class lever system with the head. The distance between the head to the spine is 0.55 meters in this posture. And then lastly, the extensor muscle to the center of the L5. This would be the fifth lumbar vertebrae. This would be the first sacral vertebrae. The distance between the center of that joint out to the extensor muscle operating behind the spine is a 0.05 meters. Okay, so we have our forces. We have our distances known. The only unknown will be E, and so we'll be solving for that extensor muscle effort. Okay, so that's the first thing we do. So putting this system into our lever system, we have our fulcrum at our L5S1 joint. We have the load of the head. Load of the head, we had that as being 50.4 newtons. We had the distance between the head and the fulcrum as being 0.55 meters. This is going to get messy, kind of sorry. But so we've done the head first. Now if we do the arms, the weight of the arms is 30.6 newtons. And the distance between the arms and the L5S1 joint is 0.3 meters. Next we have the torso. Its weight is half the body weight, 300 newtons, and its distance is 0.13 meters. Those are all going to cause the body to rotate. The front part of the top of the body above the L5S1 joint is going to cause it to rotate counterclockwise. So those will be positives. Behind the L5S1 joint, a distance of DE away, DE was 0.05 meters. So that's a distance 0.05 meters. We have E acting. Okay. Notice that how they've identified this problem. Again, the problem I stole. They had this distance as being perpendicular to the extensor muscle. Okay, so this distance is perpendicular because it acts at an angle. Otherwise, the distances to the torso, the arms, and the head are also perpendicular distances to these forces, since gravity is pulling those directly towards the ground. Okay, so we've got everything. Just to set up the problem, it will be the sum of the moments is equal to 0. We have the moment of the head plus the moment of the arms plus the moment of the torso plus the moment of the extensor muscle. Those will be equal to 0. As we said, the moments of the body weights are counterclockwise, so those are going to be positive. The moment of the effort is clockwise, so I've already put that as negative. We go back to, for an individual moment, we know that's a force times the distance, and so we have the load of the head times the distance between the head and the fulcrum, plus the load of the arms times the distance between the arms and the fulcrum, plus the load of the torso times the distance of the torso to the fulcrum, minus E, the muscular effort, times the distance between the effort and the fulcrum. Those are equal to 0. We plug in all our knowns. Our load of our heads 50.4. times the distance, 50.4 times the distance of 0.55 meters, plus the load of the arms is 30.6 newtons times a 0.3 meters, plus 300 newtons times 0.13 meters, minus E times 0.05 meters is equal to 0. The only unknown here we're solving for is E, and so using your algebra, you can find, in solving for E, you find that E is equal to 1,518 newtons. 1,518 newtons. Okay, so our muscular effort is 1,518 newtons. To take this one step further, we're looking at potential for injury to your lower back. NIOSH has set limits on allowable compressive force, meaning a squeezing force on your spine. They've set limits on basically safe and unsafe. And so when it comes down to looking at material handling types of episodes, we want to make sure that the compressive loading, the force on your lower back, doesn't exceed NIOSH limits. And so we have to take that moment equation when we calculate the muscular effort. We have to take it one step further and calculate this compressive force on your L5-S1 joint. So on L5-S1 joint, and that's really on the intervertebral disc between the fifth lumbar and first sacral vertebrae. So we're looking at that intervertebral disc. Define compressive force. Compressive force. I'm going to set up my lever system again and just put the loading, so the weights of the head was 50.4 newtons, sorry, not pounds. Whew, that would be a big head. 30.6 newtons for your arms, 300 newtons for your torso. Your E was 1,518 newtons. Operating at an angle of 30 degrees. It's an angle of 30 degrees. Note that that's an angle not with a horizontal. In this case, the problem gave it an angle from the vertical. We want to find out if all those are pushing down, how much is it squishing your intervertebral disc at L5-S1. Essentially, if all that's pushing down, you have to have, if your body's not sinking into the ground, you have to have an equal and opposite force pushing back. And so all those are pushing down, you have FC, compressional force, pushing back. Okay. So we need to find out all the forces that are directly going downwards. Directly downwards. That's creating this compression on your lower back. And so we're doing the sum of the Fy. So it's the up, down, the sum of the Fy are equal to 0. All these things that I've got on my drawing that are going directly downwards have to sum to 0. And so that means that you're negative 50.4, you're negative 30.6, and again these are downwards directions, so that's why they're negative. Negative 300. Positive Fc pushing upwards. And then minus the EY, so just the Y component, the up-down component of the effort, all those are equal to 0. EY, so just this EY is equal to 1518 is your hypotenuse. Your Y is, you're going back, is that your adjacent or is it your opposite? You can see it's right beside the 30, so it's your adjacent. Adjacent is that sine or cosine. Adjacent is your cosine. So EY is cosine of 30. And so we can cross this out and substitute in a minus 1518 cosine 30. Okay, which means that if I just rearrange them, your FC is equal to, do my algebra here, FC is equal to 50.4 plus 30.6 plus 300 plus 1518 cosine 30. We can see that's equal to, plug it in your calculator, 1695.6 newtons. Interpretation on that, we did solve the problem, did find this. Interpretation is that, is this okay? Are we going to rupture, herniate something, this intervertebral disc? NIOSH says it's okay. NIOSH okay if less than 3,400 newtons. And so a person's unlikely to injure their back if they momentarily hold this poor posture. One thing I do want to note though, the compressional force of 1695.6 newtons If you compare that to your body weight, so if you divide it by the body weight was 600 newtons. You can see that just by stooping over, if you divide those out, that's 2.83 times your body weight. So 1695 is 2.83 times your body weight. Just by stooping over, you're putting a lot more force on your back, and that's why it makes you more susceptible to injury. Not in the short term, instantaneous, it is less than 3,400, but over the long term, this continual compression can affect your back. Okay, so that concludes this lecture. As I'd mentioned, one of the homework problems, I think the final homework problem, does throw in a load on the hands. What if the operator is holding a 10 Newton load in the hands? And so you can see it's going to be the exact same problem, except you're going to add a load in here, which on your lever system will add in another load out here. And so it's the exact same thing, but just adding one more force to this problem. At this point, you've listened to the lectures, you're doing the homework problems. The homework problems have short answers, they have worked through, step-by-step answers, so use the ones you need. You're taking a quiz on this material, and you're also doing an application on this material. So contact me if you have problems. Otherwise, good luck, and I'll be talking to you again next week.